And once you're on there, since I think I see the icons on all of you guys, click on, let's see, I think you just click on, or you just go down the page and go to, yes. You click on the link, quick start, or just click on the wiki page. It'll be the same. You just click. So you were home, so click on the wiki page. It should give you this. For Alfred, using this link will be more stable. Just copy the open, fire up out, that out, and just copy and paste that link on. So you fire up out, and just copy that link.
I see the packages as soon as I know which one to do.
Yeah, so just paste that link on down and just hit enter, and it should download and get things going. We're doing quite a bit of things that you'll be able to run it afterwards using this web page, like some examples I mentioned earlier. Yeah, most of them are already spelled out in these pages, and I'm kind of running through them actually too, so to get you going essentially. Okay, I'll just briefly talk about what the input form is. So if you can follow along, just going on the site. Essentially, okay, now I'll start with the real basic. It's called kftrack. Kftracks use just that long, and the reason why it's still relevant to you guys, even though you can use SST later on or more sophisticated stuff, is because it's so simple. It's like just using that long. You can use it for your spot tag data, which is really recommended. So actually, I was in North Carolina just early in the month, and there were some talks about for meeting on animal movement. So those groups are usually terrestrial and bird person that use a lot of the Argos service for the spot related, almost like spot text. The bird text is basically spot text. And with the switch from Argos from the least square into common filter, now they are turning on common filtering by default. So unless you specify not to use common filters on the surfaces, you are you won't get least square. And I think it's getting technical here, but you actually can, if you choose least squares as your delivery method, you can ask them to do Argos. They can do common filter processing afterwards. You just have to pay more. But I don't think you can go the other way. If you request for Argos to process your data with common filter for the positions, you probably cannot get least squares afterwards. So as a user, if you want to do that option, maybe you can stick with least square, and then if you need them to do their common filter processing, you can do it as afterwards. And yeah, the second point for that is there are new studies on comparing least squares and the Argos common filter processing. Argos filter definitely make it better. And if you dig through those like 2 free papers now, the key point being, if you know they have different location classes. So you have A, B, Z, and 0, 1, 2, 3. So the improvement for the common filter processing, they gives you one message position. So for least square, you need at least 3 messages, if I remember correctly, 3 or 4 messages. And if you don't get 3 or 4 messages, it won't give you a position, or it will assign to sets. So what they have improved mostly is allowing just using one message to provide your positions, and those end up in the class B. So the location class B now for the newer processing include that particular setup, and a lot of the improvements come from just having that location class B positions with using one messages. So that's the distinction. But in terms of correcting the track, a lot of research shows you can do your own filtering afterwards, and it will be the same, if not better. So as a user, I would be I'm more inclined to be, okay, so if you just give me least square, then I can still do my own type of filtering. It can be any methods. It can be similar, it can be a simple common filter like the kftrack, or it can be more sophisticated like the BSAM or all the other stuff that's out there that's dedicated to do processing of spot related data. So you have that option, or you can just do the Argo CLS common filter. So that's the distinction. Like if you want to know what exactly you get, and then do these squares. If you don't want to bother with it, then just use the common filter from Argo. So that's what I learned essentially. And sticking along with, I want to know what's exactly going on, then it will be using kftrack. And that would rely on the start and end point, and then the track. So your input data is really a simple frame. You can use any editor of your choice. It can be in Excel or wherever. You need to get it into a flat format. It will be a flat file with 5 columns. And will be day, month, year, none of that. The only complication here is longitude goes from 0 to 360. So if you have been using -180 to 180, then you set at 360 when you are in the minus zone. So that's the only that's the requirement for that long for all the programs. It will be going from 0 to 360. So as soon as you have that file, that's all you need to run the model. And I'll show you a better example using an example data set. But essentially, the way you do it, in R, you call up the library, and you read in a data file. So this is already read in. So okay, so track, this is what I already read in. But essentially, you're reading your data file. That data file will look like here. And you set header to be true, so it has a header. And once you read in the table, and knowing that it should go from 0 to 360, then you'll be all set. And all you need to do is call up the main program, call kftrack, and you run it. And once it's finished and model converge, you can plot the fit. So that's the basic setup. As soon as you got the data file read in, you can just run it as easy as that. And I'll just show, I'll run through an example script right now, but those are the steps. So the hardest part is definitely getting the file in correctly. And that's why I mentioned the database management side, which I'll try to, because we still have some maxed out, but I'll at least get this part through, and maybe later today or even tomorrow we'll go to the database, which what that does, the database system that I've been working on and manages, like it will spill out files like that, it'll spill out scripts for you, it'll just make life easier, but essentially you're still using the same things. So I'll just go to example right now, and if I can, since there's just a few lines, we might be able to just type along. If not, I can point to you where you find the script to. So if you have your web browser open, follow me. We'll go to uncharted territory, so go to source.
Passwords.
Any password? But you should just open another tab, because I can, that's probably the easiest. But we want to go to source, and it will look funny. But essentially what we're doing, we're trying to do this exactly. So we'll have some data that comes already with the package, and then we'll just run our first track together. So if you go to source, I have a script up. So let's you go to browse. Yeah, everyone? Browse. Okay. Source and then browse. And then trunk. And there's a test script here. You want to click on it, and once you do that, it'll be like that. Details. For this first exercise, I will just have you type it in out. This is just a few lines. Like if you're lazy, you can do copy and paste. But I don't think you learn much by copy and pasting usually. And so I don't know if I should make it figure. Can you see it well? If not, just read it from your screen. But just type the first 3 lines together. I'll do the same since I won't get this. Yes. The library, call out the library kftrack. It should load and shouldn't have any problem. So once you have that, maybe you need to type library base 2. Okay. So basically, you load the libraries, simple. And we want to call the data set that comes with it. This is called big241.
Sorry, we had a warning message.
Yeah, I don't have to.
Oh, that's fine. I know warnings. I only stuck at errors. Warnings are fine. Warning is it's like a yield sign. It's not a stop sign.
Suggestion.
And then you just type enter. They should. So what it does, it loads in out your the data set, and you can look at what you have in your workspace. You do a simple command called list, ls, and it should show you actually in your workspace you have big241. And the other thing that you should aware is your working directory. Like I'll start in once I'll start, there's a directory that it will put things in. It's good to know that, because otherwise, write about where the hell is it, put it in. So the working directory. So the other thing you want to know is there's a very simple command called get we work directory. And so that's in my Mac, so it's in my home directory essentially. That allows you actually to set it to somewhere else. So usually in the Windows setting, I'll just put it into a temp directory that I have. So the set, it will complain if I do it in my Mac. But what it does, you can put it in anywhere you want. Al has a funny way of showing file path. It's do the /. So if you supply a file path, don't use /. If you do /, do double /. So do this or do double /. Like that. So whenever when you want to read in an old file or anything, you want to make sure that your file path is either double / or 1/. In our case, since we don't have to read in a data file, it's easy because we already loaded the data set called big241. So let's take a quick look at what big241 is. And when you type that, it will show you, so head will show the header, you can show the tail. It knows it's a fish, so that you can use head or tail. So you can try tail for that. It will show you the end of the file. Okay, so once you have this, you're good to go. So remember, when you have your own file, you should have the same setup. It will be a long and that. I usually name my file a bit different. I'll do long and less instead. Like sometimes you spell a bit differently. It doesn't really matter for this examples because it's simple. But I'll stick to just spelling a 3-digit, like 3-character long left. So the next one is called, we try to run it. You type fit. I usually call like whatever result that we have called fit, so it's fit. So essentially, you can use equal sign, or I usually use a sign. So you're assigning something to an object called fit. You can name it any other thing, but I usually just call it fit to keep our language the same. So fit, and then we call the main function called kftrack. So that's the main function. You have to provide input. So the first input, definitely you have to supply the data set. So let's do 5241. And then just, it has more stuff afterwards, but let's assume the default options are what we want, and you can just run it. Oh, not bad. See? You need to type. I spell my wrong. And that can choke you up for hours. I don't know how to spell. Yes, so it will run. Oh, that's it. It already finished running. And so when it works, it should, when you type fit now, if it works, it will give you, oh, my screen is too big now. Let me make it small. Okay, so this is a typical output when it works. It's like you have a fit object. Now there's a fit object of fit, and you have convergence criteria is met, and it will give you a set of outputs. So let's look at the summary. It will tell you different parameters, and you actually can get to those parameters by doing a simple $sign call. So in how to get to a sub-object, an item, sub-items, you use the $sign. So once you have the track, it's in the object, but how do you get it out, essentially? You can ask me, like, you can use the $sign, and there are different items. So what you really want is the most popular track. So you can see here. So you start typing $sign and then the most popular track. You can do a tab to auto-complete it too. Like if you start typing and then press tab, it should auto-complete, which I did just now. If not, you can type out the whole thing. And if you do that, it should give you like a long thing, which is the estimated track, the most popular track. So that's probably what you want to, once you finish running, you want to output it to somewhere else, you probably want to get that object. You can get to the other stuff too. You can call, you want to look at, say, the estimate. You just have to type ESD, like, just call, you can try any one of those things on that list, and that's basically the estimate that the model estimated and outputted. So just like what we talked earlier, you have UV and V. UV is the affection, and this is the diffusion path, and then VX, VY, bias, SX, SY, the error. So X is longitude, Y is latitude, and then that's the error structure. And in case you wonder, you can always go back to either the original publication, which you can get back from here. You see, I think the publication is here, this guy. Go back to the page, or you can, there's on this tab, you can also have the model, description of the model parameters, which would be just like a quick look of that, what those means and what those things are. And you can see here, you have the initial value, where it starts, and the unit. So that's how you kind of know what those parameters are. Because like there's no way to put units here, but so you have to go back to look at that page of binding units. And yeah, so that's your first fit. And you can do a plot. You want to look at how it fits per se. So you do plot and then fit. As simple as that one. And it should give you something like that. Yeah, so the basic recap, what we finished just now, or so far. We went through loading the data, do our first fit, and then we can access the sub-items in the fit by doing the $ thing. And then we also did a plot. So in the plot, you can see how well the data fits the model results, and I will just do it again. My windows are hiding. Okay. So the raw positions are in process. So these processes are the raw position, and the point that you deploy is a downward triangle. The point you pop off is an upward triangle, and the green line is the predicted track, and the blue line is the most probable track. The only difference is predicted track, you only have information at each step what's behind, but the most probable track, you have all the information along the entire journey. So it appears a bit more smooth for that sense. And that's what you usually do, is the most probable track. So I did mention about knowing the error estimates and having a confidence interval. So you can visualize that by changing the switch. So there's a confidence interval, CI, equals to true, or you just put T. So the true or false, capital. As long as you have capital T or capital F, you don't have to spell out the entire word true or false. So if you do add that switch, I lost my window again. So you see here now, it's falling really slow. I'm sorry. But which is good. This is what the track will be doing. Like you start off here and you're going through the endpoint, and then your confidence intervals kind of show with the cross bars and hashes. And you can see how you add those two dotted lines. Those are the confidence intervals for the model. You probably can see it better on your computer. It doesn't really show up well on the projector. But just the way to get to it is just do it by a switch called CI equals to true, and that's all you need to do. Then you can actually access that if you want to. It's actually part of things here. It takes a bit of calculations, but essentially you're using the variance of the most popular track. So that's what you get. So your variance, you can calculate the standard deviation from variance. You just do times 2 and some kind of square root of things, you can get the simple one. That's what's the input. We can get to each of those items, and yeah. And one thing that kind of housekeeping, you want to know what you did, so you actually can call fit call. Fit call will give you how you arrive at the solution. So it helps sometimes when I run a number of things, or you get fancy, you run a number of different options. At the end, you still have a fit, but how do I get to that solution? You become lost in the whole process. That's how you get to it. So, okay, I come to this solution just running the default options. So you see it here. And we can also see the initial values that we gave to the model. If you type $init, that's initial, that's on the list. It's actually all on the list, but oh, sorry, my bad. Big thing. Yeah. So data init, that's the what we use to start the model. Essentially. So if you like go through each of those, it will be UVD, whatever. So I don't have the header, but this will match up because we did not change anything, it will match up with what you see here on this page. This is like 0, 0, 100, 0, 0. This is the same. 0, 0, 100, 0, 0. And that's the initial parameter. So sometimes when you start the model different places and you just want to know how you get to the solution, sometimes you have to check that parameter. And yeah, that's how we run the first track. And let's see what else I have here. Okay, so this line, I'll just show you what this line does. This part, instead of just plotting these things, we just write it to a PDF essentially. So you have a graphical output of that. It's not essential. This is a test script whenever we install things on different computers. That's what we use to check. I somehow have an error here, but at least this stuff seems to be working, so I'm not too worried. But so there's plenty of things you can get into and out in terms of plotting and writing stuff. So this basic command just like writes something into a PDF. And since you did not specify where you save it, like usually you can put C:/something or whatever. That means it will save it to your working directory. That's why I told you to know where the working directory is, because otherwise you cannot find that for free. So you open a container for the file, and then you print it, you plot to it, and then you close the container. So it's 3 steps for how to say write something to somewhere else. You open the container, you perform your graphic component, and then you have to close the container. Then your file should be ready. That's kftrack. And the reason you want to use kftrack again is for Argos data or anything maybe too complex, you still want to know some uncertainty around your estimates, you want kftrack. That's particularly useful for the tougher cases. Like if at the end, for that big eye tuner thing, if I get desperate, maybe I'll just run that one. It's like I need something that works, and that's usually one of the easiest things to work. It's fastest, it's not really handling too much, and the basics are all there. I'll just show you a bit on basics, how you expand upon it. So one thing to look up help in out is type question mark and the name of the function. And you can see the help file. So this is what we were just trying to do. We run the function called kftrack, and I'll step you through the options a little bit. It's kind of behind the scenes stuff.
Sorry, Tim,
Yes.
This one, would we run it with the data that's already run Kalman filters? No.
No. I wouldn't run common filter on top of common filter.
Okay, so
Yes.
because that would be redundant.
Yeah, because they already run the common filter. It shouldn't look too different too.
Okay.
Like you can run 10 common filters, so they all look similar onto each other.
And the other question, on the latitude case, fine, but on the longitude, the mean and the confidence intervals are all on one side of the data.
Let's see. Oh yes. So that seems like there's the model thinks that there's a really strong bias to it. So now you can see you can rerun it and turn it off and see how different it looks. But the model itself, it looks like there's a strong bias to it. So that's the option. Yeah. So you can start playing with options at that point. So right now, so it's saying. When you look at the help file, I'll just step it through quickly. What we did just now, we run kftrack and then the data, and we close the parameters at that point. So we're trusting the default stuff to be there. And I mentioned about the initial values, so the 0, 0, 100 stuff. I was mentioning that they're all written out here. So essentially, you start out from here. The initial value for U and V, which is the action part, is 0, diffusion is 100 nanometer, so they're all written out here. So if you want to change something, you can easily just copy that path and add it to after data column, and then you just use different things. Essentially, what it meant is, if you do so you start adding your stuff. So the initial values, maybe I will just go for much bigger diffusion, would be that. So that's how you change the initial values. You can use the help file to help you along how to add these arguments. So you're doing that more complicated stuff. So okay, so I'll go through this first line. So the first one is saying text equals to true. So if the start position is known, it's true. So there are occasions that you say I'm not sure, like you can put false there. So but of course when you know the start and end point, your track will look a lot better because there's something to grant the estimation. But there's an option you can turn it into false if the occasion arrives and you need to test it out. The different ways to do it, you can do both true first, and then you can turn turn the last point to be false. Say you don't know exactly where the tag pop off, and you can do that one scenario and see if the model converges. So the first two is fix first and fix last. They're described here further along in help out, but I'm just going to do verbally for you. Theta active or theta initial is basically just a quicker way to show these things. So instead of typing them out, you can be lazy and just put it into a factor. A factor is just like a set of numbers that you use. So we assign it into a thing called theta active that will have all these switches. So active meaning you want to estimate it or not. So it will be turning parameters on and off. If you turn on all the parameters, it will be the full model. It will be the most complex. If you turn everything off, it won't be a model. You still have to turn at least one or two things on. But like you can turn things off to simplify the model. And so that's the default setup. So if you look at here, it's saying the U, V, B are active, they're all true, so meaning all these are estimated by the model. Bias, active, all the other things, all these are active. So you see, default model is turning everything on. So if your model does not work with the full model on, you want to simplify it, you can set one or more to be false. And you can do it either through this argument. So essentially what this right now is saying, this theta active equals to C is will be 1, 1, 1, 1, 1, 1, 1, 1. So you have 9 ones here. And the same with initial values. So essentially you can start from here. It'll be U init all the way to here. E scale init equals to 1. So these are the initial values for the model to start running. The final estimate will be different because it's estimating. If you don't estimate a parameter, it will be just using an initial value. So it will be just fixing certain parameters. You can play around a bit more with fixing things. Only when you come across difficult situation, you cannot get it to work. Then you either so my strategy would be first turn off some parameters. If it doesn't work, then change the initial values. Or the order can be different too. Like sometimes it just depends how I feel like. That's why sometimes it takes a month. Because whether you feel inspiration or like some days you are not inspired at all. Like everything you try failed, and it's like okay, let's do it tomorrow. And you come back and do something right, and the model get to the right place, and you have the final solution. So that's it's not really a voodoo magic, but it depends how each case is differently. The final result is always the same, if not like exactly perfect. The solution will be there, but how you get that sometimes can be elusive. So that's the trick here. you can run different models on the same data set, and you can just plot different things together and see how they look different. I'll do some small plotting routine afterwards, so you can just visualize them more easily. But you already got the basic workflow ironed up. We'll go back to here. So your real workflow is really just make sure you get the data on. We skip that part by loading a default data set you already looked at. We can spend some time just reading in your file, or I'll let you struggle it through when you play with the data that Enrico has. So I won't deal with it. You guys come up with your own way of getting the data in. And then we'll do some sample data set in a bit too. So that should help out. And then you run the main function. Here is kftrack. You get a fits object. Once you have the fits object, if it's converged, you can look at the track, you can look at the plot, and those are afterwards capture graphical output and visualization stuff. So that's it. You learn everything. We'll start through now the more with sea surface temperature matching and all the other stuff. We probably can run one more quickly. Okay, so the next up is called, so kfsst and ukfsst are very similar. So kfsst is an early iteration. So we just use ukfsst because it's just essentially similar model. And ukfsst. So it's uncentered common field pairs. It's got a really exotic name. Okay, and to test it out, this is even simpler. Like we'll just look at all you need to do. There's an inherent example in it. You can just call it example Blueshack. You run everything in one go, and hopefully it works, and you have something. If not, we'll struggle through it along together. And again, you can see it's a similar workflow. Right now, you have an extra column called SST. I don't know, what dish is this one? Maybe there's a more. So you have another column called SST, so not just 5 columns, now you have 6 columns. I'll remind you again, the longitude goes from 0 to 360, so if the data is minus 180 to 180, you have to add 360 to your minus portion. And okay, so the workflow now will include a step with sea surface temperature. I'll just scroll it up a bit more. You load the library, you can type yourself or copy and paste. Then you do the read table thing. Again, make sure it follows that structure. Now there's a step. We have to download some remote sensing imagery from elsewhere to match against it. So the tech is seeing certain temperature that we want something to match against. So that's that to download the imagery. The default option goes to an NODC site, so managed by NOAA. Not NOAA, I forgot who, but one of the atmospheric agency, and they will allow us to download the remote sensing data, and it's using the 1 degree randoms. You can go back to the paper to look at how different resolution imagery may change it. But by default, as I told you, the philosophy is trying to start from simple to complex. So the SST that we use will start from really cross to fine scale. So, and as you know, computational time will increase accordingly. So that's why our default option is to use something simple. You can get as high resolution SST as you get, but you'll grind the whole thing to a halt, and if it doesn't converge, then you have to start the process once over again. So it's a trade-off between computational speed and your patience. It's not so much time, it's more your patience. So if you run that line, you'll start going to the web to download stuff. See, so I'll run it along with you. this guy. Okay, so here, let me type along. Library, ukfsst, and then you want to load the data set called blue shack. There's a blue shack here. Yeah, they're blue. And you can do head and tail again if you want to. This shack is in Hawaii. And I want to do a step with the SST. So we specify a path where we download the SST. Can you see well? I hope you see well. Then you'll get the function called get SST from server. And then you want to supply your data frame to it so it knows basically the bounding boxes, how big is the area that you're trying to cover, the dates for your imagery. So once you get that, go.
Is this server that does it have SSS data for the whole world?
Yes.
Oh, nice.
Yes, that's why we have to use a web server. So it's doing that. The first few steps, like it has some, it's requesting some URLs to get the right data for the right time frame and area. So once they're finished, it will tell you actually download the SST files. They download from actually the link that you requested, the central processing of the files, and it will write to this directory. And somehow, if you go to that directory, you can see the files. When you don't specify anything, which I didn't specify anything.
Yeah.
So here you see I did not specify where to put it. It will just put it in the temporary directory. Because it's like for anyone who's lazy.
Even if before I already
Exactly.
set it up?
Yeah.
Okay.
Yeah, so like this, I usually assume people don't want to mess with where they put the file, so it has to be put somewhere. So it will be in a temporary directory. And the program will know exactly where the files are, so you don't have to worry too much about it. But since you asked, say you have you download big data set, you don't want to go to the web all the time. You want to work it off the web. Then you can actually supply an argument. You can put I think it's called folder SSD folder.
Ja, to web is dan.
So that should be a switch called folder. So what we did just now, we put SST from server, blue shaft. You can add a comma folder to somewhere. You can put, I'll do one example here.
You put the old.
Yeah, so you here, instead of, you add a folder equals to something. So it can be, I would say here, then it would just add it to that folder. And so you know exactly where you put it, and if you want to save it for running it later on, you don't have to go back to web all the time. Usually it's pretty quick, so only when you're dealing with large data set or you want to work on the plane, then you want to save your files and do it. I don't recommend working on the plane, because people have scary look at your computer. Like, what are you doing? So that's how you use folding. So it's like you will save it to my temporary directory and use find an SSD folder if you do that. Or you can specify it to be your working directory. So we can mix and match and do our tricks like this. So remember we learned earlier, you can just use this function called get working directory to show what's your working directory. You can actually feed it into this command. Then your folder will be in your working directory. You'll find your SST folder. Or you can do something, a good habit of programming. It's like, okay, I'll say it's like my folder, my lovely folder equals to working directory. So here now you're assigning to your working folder to here. And then you can assign, then when you write that, your folder is equal to my lovely folder. And the reason being then, if you have a specific location in the system that saves all your SSD files, you can just keep going to the same place to look for it. That's the only reason why you do that little trick. Okay, so now we have the SST files. You can see, let's check. So in my workspace right now, that will be I have my data set. I have my SSD file, which basically, since we downloaded the SSD, is already in there. And okay, so once we get that, we can run the next one. So you just type it. And then now we're calling kfsst. Sorry for the strange way of, like, ideally it should be ukfsst, but they share the same thing. So calling ukfsst or kfsst is the same one. It's just a matter of which library you load first. So we did load ukfsst, so just running with ukfsst. And again, so you call the function and you just give the animal or your track. So yeah, Lucia. And if you press enter, it will start running. For Windows user, like to see all these output in between, press Control W. So you want to turn off the buffering in Windows, I don't know how else to do works, but if you, that's one option. Let me see if I can get my other computer out. Oh. Yeah. So that option I mentioned is here. Like if you have, okay, this one. Okay. So this one, buffer output, you want this unchecked in a Windows setup, so you actually will get to see all those cryptic messages. These cryptic messages in between when the model is running, if you stay there long enough, you'll understand it. It's like Matrix. So that's what I do for that whole month. I was staring at these numbers for a long time. But basically, it's just telling how the model progress, whether it's making good progress. Just sometimes, for me, I can sense the direction, whether it's going to work or not work, and modify what I want to do. But for a normal person, at least you know it's running. So that's the good part. You want to see it, like, oh, it's running, instead of the cluster. Okay, so when you once you run it on your Windows computer, probably will fail. I don't know if you have any. So warning message does not matter. Now I still call it fit. And right fit. High fit. See if you get the same kind of look from your input. I probably did not pick the best example just now because we already called our first object fit. So if you fail at this stage, you still have the fit object from the previous example. So we'll do one step to rectify it in a bit. So the only distinction between the two models, now you can see there's a sea surface temperature error, which is here, and a bias SST, and then a radius. So you have this model include SST and these three parameters and introduce and estimate it. So see if your outputs have all these three together. How are you two doing here?
Mine didn't run.
Yeah, perfect. So that's why I want you to see actually. It runs on my Mac, but like that's the typical, like one of the two typical error you see. When it fails, you see convergence was not met. Okay, so I think most of you probably get a fail message, and this is one funny thing. Like across platforms, sometimes how you start the model will slightly be different. And I don't know, I can't really understand why. It's like it's probably a reason of the random number generated between systems that are slightly off, and that might throw you off. But I do have a solution for you. So we'll go back to source. Yeah. So this tab, and you have this script called test UKF. Open that guy up. And let's see here. Okay, so you have the full model, that's not why. Now you start making small tweaking to your file to get it to work. To your call, to your function call. So what we did was the first 4 lines, and they were failing, and then we have to make some adjustment, and that's the line. So turning on 2 biases. And try run it again, it should work. And you can repeat it now from plotting the fits, and you can see now it includes a different panel with sea surface temperature on. And remember the switch to turn on the confidence interval, try again. There you can do the plots, and that would be a success for the morning. We can get it.